This video is the middle one of a three-part series on engineering or mechanistic description of food quality. Previous video provided an overview of the framework, this one. And now we're going to build the framework, the quality prediction framework or the mechanistic understanding of quality for nutrient content or color or texture or flavor. And then once we have done them, then we make the point that the framework is kind of universal, or it can be applied to a lot more situations. So we start off with the nutrient content. Let's look at one of the simplest possible scenario for quality prediction. This idea has been around for at least 100 years. So here we have a can of peas, and we want to predict, or we want to get an idea of how a nutrient, in this case let's say vitamin C, is destroyed as the can is heated. Now for the moment we will not get into looking at the content as a porous medium, which it is. Let's just think in terms of like mashed peas. So we don't get into the porous media, those kind of process details. So in the can, as it's being heated, so it's hot here, then the location near the surface is going to change temperature more easily. So the temperature profile at A could look something like this, whereas B, that is inside near the center, at B the temperature profile will trail A, and it'll go something like this, and they're all approaching the surrounding medium temperature. Now destruction of vitamin C has been shown to follow a first order reaction. So the first order reaction, you notice that the rate kinetics, the rate of reaction is temperature dependent. So higher the temperature, faster is the destruction. So then at location A, there's going to be more destruction. So if I plot concentration of, let's say, vitamin C at A, it can look something like this. So this is concentration at A. Now because B trails A, because temperature at B is always lower, it will not destroy as much. So at B the plot can look something like this. And that just shows how nutrient content is going to vary throughout this can, let's say. So then for practical purposes, we want to know what is the average amount of nutrient. So then after having these kinds of values, we can do some sort of an averaging. Let's try to generalize this idea. First, there was a reaction, this one, then the process, temperatures varying from between A and B, and then some sort of averaging. So here is how we generalize. First, there is the local quality kinetics, which means we know the first order kinetics for vitamin C destruction, and that's given by, let's say, the first order reaction. That's local. Then we integrate that with process. So we the local kinetics, we integrate that with process, meaning uh, meaning the temperature everywhere. That will come from the process physics. So we combine these two to get basically the concentration of vitamin C everywhere inside the can at all locations and all time, but nobody cares about such detailed values. So what do? We go for some averaging. So we have these two now, but then we want to go for averaging, and so we combine the local kinetics and process, and then we do this way of averaging. This is how averaging is defined in this case, very easy, but some other quality characteristic will see that averaging is not so easy to define. So in this case, the framework consists of three parts: local kinetics, and that comes from chemical reactions, understanding of how this quality factor changes, typically almost always from experiments, and then you combine that here with process, and then finally you do some sort of an averaging. So we can just say averaging, average overall quality. Now I want to spend a bit of time showing how do we combine these kinetics and process. My idea is not so much getting into the computation, but by showing the details, it might make it more clear exactly how we are talking about combining in this framework. So I'll do that for two situations. One is a solid and the other is in a flowing systems, both in a container, unagitated, and so this is the simplest situation one can think of. And so let's look at the first one. For solid, then I have the process model is just heat transfer in solid. So then that will be described by heat equation. So heat equation is going to give me these temperatures. To that, I want to combine the quality kinetics. So in this case, the vitamin C degrades as first order. So I want to combine this temperature with that kinetics. To do that, I will actually start from, interestingly, a transport equation thinking of the nutrient, the vitamin C, as a species, and do the species transport equation or the diffusion equation for the nutrient. Now, that equation is same in form as the heat equation. If you are not familiar with the transport equation for a species, there is a separate module on single phase transport as part of this video series that I would refer you to, and if you are familiar, then you know that the transport equation would be something very similar to the heat equation. So I will start from there. Why? Just in a second it'll be obvious. Even though I start from this big equation and so on, then I say that the diffusion term I drop out because I'm saying the nutrient is diffusing inside, but that's very small. Also, in the solid, there are no velocities, so the convection term drops out. So you notice that now you have an equation that is this, it is the first order equation as we need for this kinetics of vitamin C destruction. So we combine this equation. You notice this has a temperature in there. So that temperature will come from here, and you combine these two to get quality everywhere inside this can of the solid food. If we know vitamin C concentration everywhere by combining these two, then of course we can get an average. Now let's move into the flowing system. So in this case, it's a can of liquid, and when you heat from there, when you heat from here, then it will the liquid will start to flow. So the process physics is described by the heat equation and the flow equations, because heat equation now has velocities, and the velocities will come from the flow equations. And so now one interesting question I would like you to ponder: can I now stick a thermocouple and let's say measure temperature at one point versus time? Can I use that directly to get quality or vitamin C degradation at that location from temperature versus time at that location? Take a minute to think about that. For now, I will get going. So the quality here would again, we will start from the species equation, and in this case I have dropped the diffusion term here. That one has been dropped, but I cannot drop the flow terms in this case because fluid is indeed flowing. So again, if we combine these two, all of these, then I can get quality or the vitamin C content everywhere inside the can, even in a flowing system. So from there I can get the average. So in both cases, the solid and liquid, the framework is we have a quality kinetics, we combine that with process kinetics, and we get the average like here. And so that's how we can find this nutrient content as a measure of quality inside this can. Here we get into the details of how that framework that I just talked about can work for color by showing one example. Let's take color development during French fry as an example. Of course, the color development would be a function of the temperature and time. How do we describe color as it's being developed over time of the French fry? So of course, we can simply measure color using a colorimeter and relate that to the temperature. But this would have low predictability. For example, if we change the oil temperature, then how the color develops with time would change completely, and we have to redo the experiment. A better way would be to look at it more mechanistically. That gives us more predictability, and that's what the framework we're talking about. So rate of color formation is given by the Maillard reaction, and the rate kinetics of this reaction has a form like this. Rate kinetics, so it's a second order reaction. So of that, the rate constant of course depends on temperature. So how fast this reaction goes would be dependent on the temperature through the rate constant, and so we need the temperature. Where would the temperature come from? Temperature comes from the mechanistic description of the frying process. So the heat and mass transfer model for example, for frying process would give me these temperatures and moisture. So now we can combine these two. We can combine this one and this one to get color locally at a location, and that can look something like this. So you can get at every point we can get the local color, and that now can be averaged. So let me come back to that in a second. So the color scale that you see, it corresponds to the range of concentration. So this is really false color corresponding to the range of concentrations of the product coming out of this reaction. That's how we are mapping it to color. And then of course this you can see that it compares well with experimental measurement. This, by the way, is 1/4 of the cross section of a French fry. So this is 1/4 of a cross section. And so once we have this local color, it is not clear in this particular example how would we get the overall color. So after all, when we are eating these, we're not interested in local color but the overall color. So it can simply be some sort of a surface average, for example. So then as applied to this frying process, we have a reaction kinetics, we have the heat and mass transfer description, and then averaging. Together they form the framework. Now let's look at how such a framework can be used for texture. So this one. Texture is a complex property, and many common descriptions of texture like creamy, smooth, rough, lumpy, dry, crispy, or chewy, these are obviously not engineering measures. But some of these measures can be related to engineering measures, and crispy, for example, this one can be related to Young's modulus. In fact, Young's modulus can be related to a number of these texture parameters. So we are going to choose Young's modulus as sort of representative of the texture, and we're going to try to build a mechanistic framework for estimating Young's modulus. And the reason we want to stay mechanistic is the higher predictability. So if we build models this way, for example, if I build one for drying, it can work for frying. So it has higher range of predictability. This is why we're sticking with engineering measures and mechanistic approach. So Young's modulus of a French fry obtained by, let's say, having a load this way would be a composite of this harder region and softer regions. And so the modulus that would be felt for the composite is some sort of an average over the cross section. How do I get this kind of average? Now we want to build the framework for texture prediction following the analogy to what we did for, let's say, nutrient content or color. So the first part is to get what we had kinetics before, but we had in both of those cases nutrient content and color, we had a mechanistic description. Here That is still not possible complete mechanistic, but we can start from somewhere in between. So here this is experimental information on how local moisture local modulus changes with moisture. How do we get that? So we can take the French fry and take small strips from French fry at different locations, and we can measure local modulus versus moisture relationship. So this is how it looks. This is the Young's modulus on the y-axis versus moisture content. You notice that as the material gets dry this way, then the modulus increases, which is what is expected. So this information is coming from experiment, and that gives the local relationship. And now we combine this with the process physics. So what is the process physics? If this is the cross section of a French fry, so this is the cross section of a fry, and so you can see at some point during frying we have, as expected, higher moisture near the center, the red region, and bluer region and dark blue representing lower moisture on the outside. So this process physics gives me the moisture, let's say, at any location, whereas the figure to the left, this one, gives me that given the moisture, what is the modulus at that location. So if I combine these two, I get this information for the entire cross section of the fry. That is, the core with higher moisture here will have lower modulus, and the crust that has lower moisture, so it's somewhere here, it has higher modulus. So we now know modulus as a function of position or as a function of time by combining process information with this local modulus versus moisture relationship. And now what we need to do is get some sort of an average, because when we bite into it, we're not really trying to get local modulus, but what is the overall. So it's kind of an average. This averaging process in solid mechanics is called homogenization. And let's see how we do that using this cross section of French fry. Now recall that we already have a varying modulus because we know what the moisture is at any place, and we have the relationship between moisture level and modulus. So using those two together, I know what is the modulus at any point. And so I have this varying modulus based on moisture. And now I apply a virtual load, meaning in a computer model, I give this boundary condition, fix this end, and I apply a load here. So with that virtual load, I calculate strain. So using the varying modulus, I calculate how much strain is going to happen. Now the good thing is, and this is why it makes sense to talk about this approach today, it is not very hard to do this calculation of getting a a strain for this load when the modulus is varying over the cross section. So computationally these have become much easier and routine. So we calculate the strain, and from the load I know the stress. So if we get stress over strain, that is my effective or average modulus for the entire cross section. And this process, this averaging process, is called homogenization. We now go back to our previous slide, and by homogenization I can now get Young's modulus for the entire cross section over time during this process of frying. And so that should relate to something like crunchiness, for example. The point is, the process we did by combining this guy with the process and the averaging, this is fairly generic, and it can apply to other processes related to frying, let's say drying. In fact, we have done this. We first got these modulus versus moisture by drying the strips. Earlier I mentioned for frying, it's not for frying fried chips, it's for dried chips. And so we got this material, the information for dried potato material, and from that we could predict how Young's modulus for frying would change. So the framework is little more universal. That it is not just stuck to drying. It is not just stuck to one drying temperature. It's more universal, and from drying information I could get to frying, and my predictions here match quite well with experimental results. So in other words, this is more universal. The framework is more universal. To recap then, in this Young's modulus example for texture, our texture framework, prediction framework for texture in more or less mechanistic way with some experimental information is this. So we have local kinetics. Instead of local kinetics, we have what we have is the relationship between moisture level and modulus, and then I combine that with process, and then I average it, which in this case, in case of solid mechanics, we call it homogenization. So this is kind of the same framework that we already use for like color. Would the framework apply for flavor? Notice that flavor has to do with chemical reactions. So if the framework worked for, let's say, nutrient content, which was chemical reaction, color, that was chemical reaction, then it should work also for flavor. The framework, while all the pieces are there for applying it to flavor, it hasn't been done, at least not that I'm aware of. And so what is being presented is more conceptual, but it should be possible. So if we look at the framework, we start from local quality kinetics. So in case of bread baking, the flavors in bread baking, they have been extensively studied quantitatively in one research paper by Fabian, and it consists of 10 diffusion reaction equations, and so all of those equations have their rate constants. and those rate constants depend on temperature, it could depend on moisture, and so on. So then we need the process physics. So process physics for a bread baking would give me temperatures or moistures at any point inside. And now we combine these two to get the local quality. So the kinetics that is mentioned here plus the process physics gives me the local quality, let's say the local flavor. And then we need to do some sort of averaging to get the averaged overall quality. This is the main idea. So we see that the concept, the framework concept of having a local quality kinetics, then combining with process, and then averaging, this idea can work also for flavor. Now we have seen the framework of local kinetics combining with process physics and averaging. It seems to work for nutrient, color, texture, and flavor. There are cases that may not need the full framework. It may need just a small part of it. So these are special cases, and I want to share two of those. One is porosity and the other is case hardening. Those are certainly measures of quality, and we will see how we would be able to predict them mechanistically. The first one is in the context of rice puffing. It's porosity in rice puffing, and we're talking about a situation where the process physics already has a transport description with solid mechanics. So given that we can do the transport model with mechanics, can we get porosity from this mechanistic model? Why are we after porosity? Porosity can be a measure of firmness, crispiness, and crunchiness, for example. So porosity can come from the process model itself, and let's see how. So how can we do porosity prediction in rice puffing? So here is a rice grain, and we heat the grain, then whatever little water that is there, it starts to evaporate, and that generates pressure. At the same time, because of heating, the starch kind of melts. It goes from glassy to rubbery state, and it's kind of soft now with pressures inside. So that causes it to expand, and after it's expanding, as it's expanding, it's also drying. So as it's drying, it's setting the structure. So we get an expanded volume, and from the expanded volume we can get the porosity. Because we knew the initial volume and the process physics gives me the final expanded volume. So comparing the initial volume to the final expanded volume, we can get porosity. In fact, we can get it locally as the process affects different corners, different regions of the grain differently. The porosity will be different. We'll see in a second. So here we show porosity prediction from the model, the physics that combines transport with deformation, and here are the experimental results. So this is the rice grain changing with time this way at different times. So if we look at let's say the 9-second data, the mechanistic description can pick up not just over time but within the rice grain where things will puff first. So at 9 seconds it shows high porosity near the corner, and it's the same for the experimental result. And the reason for this is the corner heats first. So there the material gets softened and the pressure development happens first, so it expands first, and therefore we have this kind of a spatial variation in porosity that can be predicted, and of course that relates to quality. So, and here you see porosity evolution with time, and what you see is a very mechanistic approach to get to this quality parameter of porosity that relates to a number of the more traditional quality measurements. How we got porosity kind of still fits in the overall framework that we developed, except that it is a very special case. We don't need the kinetics. We don't need to combine it with the process, and we don't need any averaging. So it's just the process description gives the quality. So this is a special case, kind of a simple version of the overall framework. I want to show another example where process physics is sufficient to predict quality, and this one is case hardening in case of potato drying. Now the dried material, its quality is dependent on how much case hardening happened during drying. In a drying process like in potato drying, the outer layer can form a hard shell, and it can form perhaps too soon in drying. So this hard outer shell is referred to as case hardening, and that is a quality issue in the drying process, meaning it causes a problem in terms of the quality of the dried product. Now, during drying, the potato material goes from a soft, rubbery state to a glassy state. This depends on moisture and temperature. So this glass transition temperature, given here as a function of moisture, is a measure of the temperature at which this transition occurs from rubbery to glassy. This information about the material is either available or this needs to be obtained, of course, to describe the material. But given this material information, just from the process model, we can predict whether there is going to be this hard shell formation or whether it's going to be rubbery or glassy. Consider two drying processes, one at a lower temperature and one at a higher temperature of a cylindrical disc of a potato, and the picture shows this part. So it's symmetric, so it's showing this rectangle below in the pictures. The colors show the degree of this transition, the degree of crust formation. So a green color, for example, is pretty much a dark green shows no transformation at all, so it is still rubbery and soft. So what we see in this first set of curves, that is for early in the drying process, so it hasn't dried as much. What we see is for the higher temperature dry, there is more of this crust formation on the outside, which is the measure of quality, as I was discussing earlier. So the process physics alone gives me this measure of quality. At a later time in drying, what we notice is the slow drying process makes the entire material completely glassy, whereas in the faster drying material, also reaching the same moisture content, but the outer layer here is glassy, but there's still some rubbery region left, which is not the case in this one, So again, this gives us important information on the quality of the dried product, and that was obtained from process model only. But it's more than just temperature and moisture. It's another level detailed information on quality, but process model itself was sufficient along with some material details. So that was another example that fits in the framework for quality that we talked about, but it doesn't need these other details. Just the process information is enough to predict quality, and this was in the case of case hardening in drying. So to conclude, this video showed that this framework is applicable to, let's say, nutrient content, color, texture, flavor, but also we showed some special cases where we don't need all the components of this framework, just process model is sufficient.